When you write machine learning code in Python, it feels so straightforward, doesn't it? You type a command, you get an answer. But what's really happening under the hood? Well, there's this whole hidden journey. We're going to follow one single piece of data, a tensor, as it travels from your Python script deep into the hardware and all the way back.
So let's start with something that might sound a little weird. Most of the machine learning code you write in Python isn't actually executed in Python. Think of your code more like a set of directions. The real number crunching, all that heavy math, that's happening somewhere else entirely.
Okay, so here's our plan. We'll start by looking at this Python illusion. Then we'll lay out our journey map. We'll trace a forward pass, see how AutoGrad records everything, look at some common traps you might fall into, and wrap up with 3 simple rules you can use.
To really get a handle on this, we need a mental model. A map, really. This map is going to be our guide through the whole thing, and it breaks down the entire system into just 3 main layers. So, here are the 3 stages of the journey. It all starts up here, in the Python front end. That's where you are. From there, it drops down into the C++ runtime and a component called the dispatcher. And finally, the work gets handed off to the GPU kernels, which are managed by these queues called streams. We're going to keep coming back to this map, so keep it in mind. And who's the traveler on this journey? Well, that's our hero, the tensor. At its core, it's just a multi-dimensional array. This is the fundamental piece of data that's going to move through the whole system. Next up is the dispatcher. Think of it as the routing brain of the C++ layer. Its whole job is to look at a tensor and decide exactly which piece of low-level code is the right one for the job. So what's that low-level code? It's called a kernel. A kernel is a super optimized function that does one specific thing, like addition or multiplication, and it does it incredibly fast on the hardware. And how does the GPU keep track of all these tasks? There's something called a CUDA stream. It's really just a to-do list, a work queue. The GPU pulls tasks from this stream one by one in the order they were added. Finally, there's AutoGrad. This is like a historian for our tensor. As the tensor goes on its journey, AutoGrad is watching and recording every single operation, building a map, a graph, so that it knows how to calculate gradients later on. Okay, with our map and key players defined, let's trace a real operation. We're going to follow it step by step on its forward pass from Python all the way down to the hardware and back again. Let's use a really simple example, just adding 2 tensors, C equals A plus B. It looks like one simple line in Python, but as soon as you run it, a whole handoff process kicks off. All right, so where are we on our map? We're right at the very beginning and the Python front end. This is your world, where you write the code. But Python itself was never really built for heavy-duty number crunching. And why is that? Well, for a few reasons. It has some performance limits. There's this thing called the global interpreter lock, the GIL, that gets in the way of true parallelism. And honestly, the overhead for even simple math is just too high. So Python's job isn't to do the work, but to delegate the work. So how does this handoff actually happen? It's done through a special binding layer. What happens is your Python tensor object gets unwrapped. All its important info, the data, the shape, the type, is passed down to the C++ backend, which then builds a brand new C++ version of that tensor. And just like that, our tensor has crossed the first border on our journey map. It's left the Python front end and is now inside the C++ runtime. It's not a Python object anymore. It's a native C++ object living in a much faster, compiled world. So what does our simple A plus B look like in this C++ world? It gets translated into a very specific function called add. By the way, is just the name of the core C++ library that handles all these basic tensor operations. Now, the dispatcher, our routing brain, takes over. It has a checklist. First, it gets the @add command. Second, it looks at our tensors and asks a bunch of questions. Are they on the CPU or GPU? What's their data type? Do we need to track gradients for them? It bundles all these answers into a unique ID, a dispatch key. And third, it uses that key to look up the perfect pre-compiled kernel in its big table of functions. Okay, decision made. Let's say our tensors are on the GPU. Now this is a really crucial point. The way the CPU talks to the GPU is asynchronous. The C++ runtime just puts the add job onto the GPU's to-do list, that CUDA stream we talked about, and then immediately moves on. It doesn't wait around for the GPU to finish. The CPU gets control back right away so it can go prepare the next operation. This is a huge reason why things run so fast. And here we are at the final layer of the forward journey on our map, the GPU. The GPU pulls our addition job from its stream and runs the kernel on its thousands of cores. This is it. This is where the actual math happens, a long, long way from that single line of Python code we wrote.
Once the GPU's done, the journey goes in reverse. A brand new C++ tensor is created with the result. It travels all the way back up, crosses the border back into the Python front end, gets wrapped up in a nice new Python tensor object, and that's what finally gets assigned to your variable C.
So, we got our results, but the whole time that forward pass was happening, something else was going on in the background. Remember Autograd, the historian? It was watching everything, recording the story of our tensor's journey.
As our tensor moved through the C++ layer, Autograd was busy building this computational graph. You can think of it like a family tree. The original tensors, A and B, are at the bottom. They're the leaves. The final result, C, is at the top, the root. And now that C tensor has a little note attached to it, a grad fn, which is basically a memory of the addition operation that created it.
And what's really cool is that this graph is dynamic. It's not set in stone. It gets built from scratch every single time you run a forward pass. That's what lets you use normal Python stuff like if statements and loops to change your model on the fly. It's a really powerful feature.
Now, this whole system, with its different layers and that asynchronous communication, it's incredibly powerful. But it can also be pretty confusing. And if you don't understand the journey we just mapped out, it's really easy to fall into a few common traps.
Okay. Trap number 1.
Have you ever tried to time a GPU operation and gotten a number back that seems way too fast? Like, impossibly fast. There's a reason for that. It goes back to that asynchronous behavior. When you use a standard Python timer, you're not actually measuring how long the GPU took to do the work. You're just measuring how long it took the CPU to tell the GPU to do the work. To get the real execution time, you have to force the CPU to wait. You do that by calling torch.cuda.synchronize. That makes the CPU pause until the GPU's entire to-do list is empty. All right, trap number 2. You're in a loop, and you decide to just print a tensor's value, or maybe call .item to get a number out. And suddenly, your code grinds to a halt. What's going on?
These kinds of operations are what we call synchronization barriers. See, to print the value, the CPU needs the value, but that value might still be on the GPU's to-do list. So the CPU has to stop everything it's doing, wait for the GPU to catch up and finish all its work, and then get the result back. It completely breaks that beautiful asynchronous pipeline we had going.
And the last trap. This one can be a real headache when you're debugging. You get a GPU error, but the Python error message points to a line of code that seems to have absolutely nothing to do with the problem. You guessed it, this is also because of asynchrony. Let's look at our map. The actual error might happen way down here in a GPU kernel, but the CPU is already way ahead working on something else entirely up in the Python front end. The error only gets reported when the CPU finally gets around to checking in with the GPU. So the stack trace tells you where the CPU found out about the error, not where the error actually happened. So now that we've traced this whole journey and seen the pitfalls, we can boil it all down to 3 simple, actionable rules for writing better code. Just 3 rules to keep in mind. Rule number 1, profile correctly. If you need to know how long a GPU operation really takes, always use torch.cuda.synchronize. Rule 2, avoid those synchronization traps. Especially inside your tight performance-critical loops, stay away from things like .item or printing tensors. Don't break the pipeline.
And rule 3, when you get a weird GPU error, don't trust the stack trace. A profiler will give you a much better clue. And hey, for debugging, you can make your life easier by setting an environment variable. CUDA_lanch, blocking equals 1. That forces everything to run synchronously, and your stack traces will actually point to the right place. So the path from a simple line of Python to a result from the GPU is this whole coordinated dance across different layers. Now that you have this journey map in your head, the question is, where's the next bottleneck hiding in your code?